All right, everyone, in this video, we are going to discuss acetal formation. When you react an aldehyde or ketone with an alcohol, we're probably going to assume that that alcohol is present in an excess amount and that we're going to generate an acetal. Now, an acetal, sometimes also referred to as ketals if they're ketone derived, is a species where we have two OR groups bonded to the same carbon, and they'd be bonded to the former carbonyl carbon. Now, in the process of generating the acetal mechanistically, we'll proceed through a hemiacetal intermediate. I want you to imagine that we started off with an aldehyde or ketone and one equivalent of our alcohol added into the structure, and we broke the pi bond. That generates your hemiacetal, where you have an OH group and an OR group in the structure. Now, conceptually, hemiacetals can form under acidic conditions with alcohol and acid, or they can form under basic conditions with an alkoxide and an alcohol solvent. So we can generate the hemiacetal under acidic and basic conditions, but in order to drive mechanistically from the hemiacetal to the acetal, we have to react under acidic conditions. The acetal will form only under acidic conditions, meaning the acetal cannot form under basic conditions. And you'll notice that to drive from hemiacetal to the acetal, we're going to have to kick out this OH component, which would be kicked out as a water leaving group, and then you would have to add another ROH into the structure. Okay, I'm going to repeat that. To drive from the hemiacetal to the acetal, we have to protonate this OH component, turning it into a water leaving group. We then have to collapse, kicking it out, and then we have to add in another alcohol to incorporate. So let's now look at this mechanistically. We're going to take this ketone here, and we're going to react with ethanol and an acid catalyst. So remember, if we're reacting with an acid here, in solution, we're going to have a protonated version of ethanol and ethanol present, and we'll use both of those in the mechanism. So tracking with you, we know that right away the neutral alcohol, because it's a poor nucleophile, will have a pretty poor addition to the carbonyl carbon, which is why we've acid catalyzed this reaction. In the first mechanistic step, we will protonate the carbonyl oxygen. As we do so, we now have more electrophilic carbonyl carbon, and this is our window of opportunity for our neutral alcohol to attack and bond. So we've protonated and we attacked. We're then going to deprotonate the oxygen atom that just added into the structure because we want to stabilize that linkage. Now, I'm going to repeat that. Deprotonating this oxygen atom, making it neutral, stabilized its linkage. Because right now in the protonated state, what could happen is that the OH could collapse, kicking out a neutral alcohol and reform the carbonyl. But as I deprotonate that oxygen atom, I've now made that into a poorer leaving group in comparison to what it was when it was protonated. So I have effectively stabilized its linkage. That brings us to our hemiacetal intermediate. Now the hemiacetal intermediate is a good flag point, checkpoint intermediate. Now that we're at the hemiacetal, we need to think about creating our water leaving group. We're going to protonate the OH group to create a water leaving group. Now that that oxygen is charged positively, we could use the lone pair from the neutral OR component to collapse and kick out a water leaving group. H2O gets eliminated as we fold down that lone pair from the OR group. That oxygen is now pi bonded to the carbon, and it possesses a positive charge, which is analogous then in reactivity to the protonated carbonyl. This is the window of opportunity for a second molecule of alcohol to attack and bond. Once that attacks and bonds, the oxygen atom that attacked is now formal positive. And to stabilize that linkage and form the neutral acetal, I have to deprotonate in step 7. Okay, notice how net result here. We've kicked out a water leaving group, and we've incorporated 2 OR groups at the carbon, forming our acetal. And to draw that for you in the expanded form, that would look like this. We can imagine 2 molecules of ethanol bonded to what was the former carbonyl carbon, generating our acetal functional group. So let's recap this mechanistically. We know that the neutral alcohol cannot attack right away. It's a poor nucleophile, which is why we protonate the carbonyl oxygen first. Now the carbonyl is more reactive. The alcohol will then attack and bond. The oxygen now has a positive formal charge, the one that just added in. We are going to deprotonate that oxygen atom to stabilize its linkage and make that into a poorer leaving group comparatively. That brings us to the hemiacetal structure, where we have our OH group and our OR group bonded to the same carbon. From the hemiacetal stage, we want to protonate the OH component to create a water leaving group. And after that's been protonated, you would collapse a lone pair from the neutral OR portion, forming a carbonyl, and you kick out your water leaving group. The folding down of that lone pair creates this charged carbonyl, which is in reactivity terms analogous to the protonated carbonyl. That has enough reactivity for another neutral alcohol to attack and bond. Once it's bonded in, we're going to deprotonate the oxygen atom and stabilize the acetal structure. So a total of 7 steps, and that can feel a little bit intimidating, right, to have a mechanism that's so long. But I really want to encourage you to think about these mechanisms of aldehydes and ketones with respect to the theory that we're cultivating. Like we've said, the alcohol can't attack and bond right away. Okay, cool. Well, let's protonate first. Well, after it's protonated, well, the oxygen's got the positive charge. We want to keep that in the structure, so let's deprotonate. And we have to kick out a water leaving group to drive to the acetal, so let's create our water leaving group. And once protonated, that's now a better leaving group than it was before, so I can collapse and kick that out. Charged carbonyl, well, that's analogous in reactivity to the protonated carbonyl. So there's ample reactivity for our neutral alcohol to attack and bond, and ultimately we want to deprotonate that oxygen to stabilize its linkage and generate the neutral acetal. Okay, there's a logic structure that we're going to follow as we're generating our acetals. It helps us think through these longer mechanisms and do so with confidence. So I now want to show you a couple examples here of acetal formation. Let's say I'm reacting this ketone with methanol and an acid catalyst. I'm going to assume that this alcohol is present in excess and that I'm going to drive to the acetal stage. So I'm going to turn this ketone into an acetal. I'm going to imagine bonding to what was the former carbonyl carbon, 2 OR groups, which pertain to the OR group of my alcohol. That generates my acetal. Okay. And I know that 2 of my alcohols will add into the structure, generating 2 OR groups because there were no OH groups in my structure to begin with. Now, you might be wondering, why did you make that stipulation, Ryan? There's no OH group in the structure. Well, let's now look at a situation where maybe there is an OH group in the structure. If there's an OH group in your structure, when you react with your alcohol, what's going to happen is there will be an intermolecular and an intramolecular. We're first going to do an intramolecular structure, generating a cyclic hemiacetal intermediate. And then we're going to have our intermolecular, which will replace that OH component of the hemiacetal with the OR component of the alcohol that we're reacting with. I'm going to repeat that. If there's an alcohol within the chain, you're going to end up doing an intramolecular, forming a cyclic hemiacetal. And then what will happen is the OH component will be lost as a water leaving group. And you will then incorporate a molecule of alcohol that you're reacting with to generate your acetal. So let's break this down step by step. We recognize that there's an alcohol in the chain, and therefore, if the carbonyl carbon becomes protonated, that alcohol can attack intramolecularly and bond. Tracking with you, if you count from that attacking alcohol to the carbon that's being attacked, the carbonyl carbon, that's 6. There's going to be a 6-membered ring forming, wherein the oxygen is attacking the carbonyl carbon, and we break the pi bond. So we'd attack, then deprotonate, and that would then form the cyclic hemiacetal intermediate. Then what you want to imagine here is that we're going to protonate the OH group, turn that into a water leaving group, and then the oxygen of your OR portion that will collapse and eliminate a water leaving group, which will now be free floating. That creates a charged carbonyl, which kind of looks goofy because it's within the ring. This is now where we have enough reactivity for the other alcohol to incorporate. That will attack and break the pi bond. The oxygen that's just added in has a positive formal charge. We would then deprotonate that oxygen atom to make a neutral OR group. And now we're at the acetal stage because we have this OR group, and that OR group bonded to the former carbonyl carbon. And keeping in mind that this intermediate here is planar, trigonal planar intermediate, when the alcohol attacks and bonds, it can technically attack and bond from above the plane or below the plane, and we can produce here a pair of enantiomers. Okay, we did an intramolecular reaction, forming the cyclic hemiacetal, and then ultimately we lose that OH group as a water leaving group and replace it with an OR group pertaining to the alcohol identity of the alcohol that we started with. Okay. Now, that's a higher level question, definitely a little bit more difficult. Here we generated a cyclic acetal, and the alcohol within the chain attacked intramolecularly bonding, and then we incorporate one of the alcohols that we reacted with. Coming back to the former example, there were no alcohols within the chain, so therefore there was no intramolecular reaction possible. Instead, we just added in two of our methanol molecules, generating our acetal. After the first one adds in, we would have our hemiacetal, which is pictured here. Okay, and then we would protonate. We'd eliminate water leaving group, and then we'd incorporate a second alcohol, ultimately to generate the acetal group, the acetal functional group. So for right now, I would say one of the big takeaways of this video is just the mechanism of forming the acetals. Okay, acetals have two OR groups bonded to the same carbon. You could potentially have those OR groups cyclize to one another or form a cyclic acetal. The acetal can only be generated under acidic conditions. It cannot be generated under basic conditions. However, we can generate the hemiacetal under acidic and basic conditions. We have to have acidic conditions to be able to drive from hemiacetal to acetal, because we have to protonate the OH component, making that into a water leaving group that can only occur under acidic conditions. We covered the mechanism, and from the hemiacetal stage, that's a good checkpoint intermediate, we have to protonate the OH component to create a water leaving group. And then we have a second equivalent of alcohol attack and bond in. And if there's no alcohols within the structure to begin with, you're just going to add in two of your alcohols, two of your OR groups to form your acetal. And if there is an alcohol within the chain, then that is going to be able to attack intramolecularly after the carbonyl protonates. That would then form a cyclic hemiacetal, and that cyclic hemiacetal will then continue to react. We'll lose our water leaving group, and a molecule of alcohol will attack the planar intermediate, and you'll end up having your acetal functional group, where we have our OR group within the ring here, which pertains to the alcohol that attacked intramolecularly, and you'll have your OCH3 component, which pertains to the alcohol that was over our arrow.